Okay, so today's class we'll be working with we'll be creating a projectile, and then once we create the projectile and launch it, we'll add some drag force to show you how you write C files or edit C files. So there are two steps to it. The first step is to create XML, which I will show you first. And then once we create the XML, then I'll show you how to use the template I created for this for the C files and how to run that template with the projectile XML inside it. Okay, so let's get started. So what I'll do is I'll take the hello.xml example and I will modify it to create a projectile. Essentially, we'll call it ball.xml, and then we'll test it with simulate. And once we do that, then we'll proceed to the second part. So I realized that the hello XML is not in the model distribution, but you can actually go to Google and type hello.xml. And then the first result basically gives you that code I wrote down, or I shared with you last time. So copy that code. So just hello.xml MuJoCo will give you this file. So let's create a new file in. Okay, so let's go and test this. So navigate to your file, your MuJoCo within terminal, within the shell. So cd documents MuJoCo. In this case, we'll have to go to bin because that's where we run simulate. And then type simulate. Okay, and then if you drop this file, ball, which I just created within projectile, then you see the same thing we saw last time. Okay, so we've got that working. Now let's modify this to sphere. So all I need to do is change this to sphere and then change the size to, since a sphere is parameterized by a single number, the radius, I just change that to some radius. So let's say 0.1. Okay, that's the only change you need to do. And then we can go here and based on Giuseppe's suggestion, you can actually do reload, which is much easier than dropping it. So that's it. So the ball drops. Okay, so that's all. Okay, so we did step 2, but wait, there was something else which I wanted to show you. Actually, let's delay that till later. There is a way in which you can view that XML file in a much easier way by doing print model within simulate. But let's do that later on because we need later on when we do the write the C file. Okay, so the next step is to create the makefile, write a C file, and create the executable. So here's where I think I've made life easy by creating this template. So what I want you to do is go to tiny.cc /MuJoCo. You should see a file called template.zip. Unzip that file and drop it in my project. And once you drop it in my project, you rename it as Projectile. Now in this case, we already have a folder called Projectile. So in this case, you just need to take the contents of template and dump it in Projectile. So if you unzip the file, you should see a list of files in that. So copy all these files and then go to the folder you created, which is my project, projectile, and then just drop these files. Okay, now we don't need hello.xml, so I'll just delete that. Okay, now there are a few things you need to do once you do this. For this to run, you need to do 3 changes. Okay, and this is true for any new project I'll be working on. I will copy the template file and work from them. So every time you need to do 3 changes so that you can get everything working with MuJoCo. Okay, so there are 3 files you need to work on. First is main.c. So open main.c Okay. In main.c, go to line 13 and change the from template /hello.xml to projectile /ball.xml. So it's right here, line 13. All I need to do is change this to projectile. Okay, so clearly this is a folder. So if you had called it something else other than projectile, you need to call it appropriately. And then this is the XML file we'll load. And you have to be careful here. This assumes that in your MuJoCo distribution, you have created this file within the MuJoCo distribution. There is a my project folder or some folder. It doesn't have to be called my project. If you call it something else, you need to change that here appropriately. Otherwise, this will not work. So go to my project, and within that, there's a projectile folder. And within projectile, there is a ball.xml. So that's the first change. Okay, the second thing is you need to open the make file, which I've also provided here. Open the make file. Okay, now you see that in the make file, there are like things which, but first of all, in the make file, you can comment out items in the make file, each line by using the hash. Okay, now I'm using a Mac system, so I have uncommented the part for Mac, that is common libs and cc. Okay, if you are working on Windows, what you want to do is you can, if you want, comment these up with a hash, and then uncomment these ones for Windows. Okay, if you're working on Linux, then you will want to comment out the ones for Linux and comment everything else. This is just so that it works with your operating system. So that's the first step. The second step you need to do is, again, you need to tell this make file that the root file which you're working under is called projectile. So you need to type that. Okay, so assuming that you've done those changes, uncommented the right commands for your operating system, and replace root equals to projectile, you can close that. And then the final step is you need to open one of these two files depending on your OS. So if you're using a Unix system, which is in this case Mac or Linux, then you want to open this file. I just right click and say open with TextEdit, which is the Mac software for opening text files. You could open it with WordPad or any rich text formatting editor. And here you also need to, unfortunately, change this thing to projectile. Okay, so if you are running Windows, you want to open this bat file. This is basically an executable file. And then you will change this from template to projectile. Okay, so I will not be using this because I have a Mac, but if you have Windows system, use this. Okay, so you can close that. So that completes these three steps, 1 through 3. Okay, now we are all set to run this projectile folder. What you need to do is we will navigate to, we'll use the shell, we'll navigate to projectile, we'll type ./run main. That was the Unix file, if you remember. My bad, this should be run Unix, because that's what I called it. Or you should run win in Windows. Okay, and remember, in Windows you want to use the x64 shell. You don't use the CMD. It'll probably not work. So let's do that. So in the shell, we go to the projectile folder. So cd my project, cd projectile. And then if you want to check the contents, you can do ls. So it tells you all the files. And here we type make. Sorry, not make. You do run. Well, you could do make, in which case it'll build the files. But by running one of these run Unix, you're actually doing compiling and you're also executing the file. So you'll run, so let me just show this to you. So actually you're doing a bunch of things. You're first resetting, actually that doesn't really work on Mac. You're cleaning up this I think cleans the any object files, .o files. Make basically makes the file, and then it navigates to a folder bin and then executes Projectile. And that way you really don't need to go to bin and then execute it. It does it for you. Okay, so let's run Unix, then enter. Okay, so you saw that it basically did the same thing, but now it did not have to run simulate and drop it. Basically ran the main.c file to do it. Once we got this working, which is kind of important because that's what we'll be doing for the rest of the course, then we will basically modify this file to suit our purpose and make the animation do to actually throw the projectile stuff, dropping it from a height. Okay, so the next thing is, let me open my presentation. Now, just as we had seen the XML documentation, there is an API reference documentation. It's this link, which I will put in the chat. Let's look at this main.c. That's the file which actually runs the code. And it opens the ball.xml file. Okay, there are 3 things I want you to know, and these are like universal. This will come again, and you don't really need to modify anything in this file really when it comes to these functions. But I think it's important that you understand these 3 things. So I'm opening main.c. Okay, and you can just look at my screen. So the main thing here is that there is a model and there is data. Okay, and they're different. M is the object to the model, and D is the object to the data. Now there are other things like camera, op, scene. These are all objects, and we'll be modifying some of these. A lot of the code sitting inside main.c is actually for animations and visualization. So this is all for visualization and controlling the speed of the animation. So for example, keyboard, we never even touch this. Mouse button, we don't touch that. Mouse move. Scroll. Okay, the main part of the program which we are interested in is main. Okay, in main, first of all, you can see that it uses that key which we dropped last time. It opens the XML file. So MJ, if it starts with MJ, that's a MuJoCo function which you can find in the documentation, the API which I just opened. It loads the model based on the path I gave, which is up there. Then using the model M, okay, model is basically the XML file you wrote. It creates data, and so the data structure actually keeps track of the state. So for example, the model has the position of the ball. So it could be X, Y, Z position, right? That's what the model has, but the data basically keep track of the actual value for the X, Y, Z. So for example, X equals 0, Y equals 0, Z equals 1 meter. So that will be kept in D. You don't have to really worry about this. Is all animation stuff. Don't worry about all that. The main heart of MuJoCo is this particular infinite loop. It's a while loop which executes one integration step, which is denoted by as MJ_step. So every time MJ step is encountered, it basically integrates the equations from one time step to another time step. Now, the time step is something which you can define. You could have time step of 0.01 or 0.001 or 0001. So the smaller the time step, the more accurate is the simulation, as we will find out when we do some of the other things in this course. Okay, so that's the key step. And then again, it's once you take a step, you get a new configuration for the objects in the scene, and then you need to update the scene. Okay, so that's done here. Okay, and so for all practical purposes, we will write code pretty much here today. We will not do additional functions. Now, now that I've explained that, let me just give you a summary of what things we'll learn. Okay, and I'll show them to you. So these are some of the things we'll go through today. And I think I should have enough time for this. And I'll go through them one at a time. And then, now they will not make sense, but as we implement them, it'll become, it'll be a handy reference. So let's start off working with main.c. So the first thing we notice is when we run this command is that we might want a different view, right? And it's kind of annoying, it's zoom. So what if I move this ball to 5 meters? If I move it to 5 meters, I won't even see the ball. So if I go to ball.xml and then change the starting position to 5 and then run it, so I don't even see the ball unless it falls down. So maybe a better view for this is this, right? Zoomed out view. So there's a way you can change the viewpoint in the main file. So this is what you need to do. Go to main.c. And actually, I've done some work here for you. What you need to do is just after the line mjr_renderer, you see a printf. You uncomment that line. Okay, and this is going to print a few things. It's going to print the azimuth, elevation, distance, and these are basically the X, Y, Z location at which the camera is posted. And all these things are within an object called cam, and that's, if you scroll up, I'm going to quickly scroll up. Right here, it's basically camera options within MuJoCo. Okay, so let's go back to 184. That line is defined. Okay, so please uncomment this and then run this program again. So line 84, renderer, uncomment that one. Okay, so now you see it's printing something. It's actually printing that cam.azimuth and so on. And so what I'm going to do is, so remember it's 90 minus 45. I'm just going to zoom out. You can see as I zoom out, this actually changes. At least this changed. Okay, if you want to change the view, for example, this one, then you see it's changed. So what I'm going to do is I'm going to stick to this view. I think it was 90. The default was fine. It was 90 minus 45, and I think it was 2, but I want to change it to 3 because that gives me a zoomed out view. So I'm going to close this. I'm going to comment this back. Now, I've done this already for you. So comment back line 184 and go to line 156 all the way to 162. Okay, so we will uncomment that. And then you can put whatever you want here. So we figured out that good configuration is 90 minus 45 and then 2. So this is basically setting up these 6 numbers. Okay, and we just adjust it by using the GUI. So keep it uncommented by changing this 90 minus 45 to rest remains same. And now run this. Okay, it's didn't change. Hold on. Let me redo this. So let's go back. Like this. Zoom out. Oh, 3.44. Okay. Yeah, I should have put 3.4. Let's put 4. Should work now. Okay, still it looks a little bit high, but that just gives you an idea. I'm just going to go back and put that from 5. I'm going to put it back to, let's say 3, and see if it works. It's a little bit high. Just change it to whatever it was. Okay, I'm going to launch the projectile high up, so I need it to be a little bit high, but not too high. So I think this is fine. So I'm going to go back and comment out 184 to not show me the. Okay, so that's changing the orientation. Okay, next let's see. Okay, what should we do next? So next, what about gravity? Can you change gravity on the fly? Now, I showed you that you can change the gravity by going here and typing up gravity as 0, 0, -1. It was slowing down. But you can actually change the gravity in code also. So I'm going to show you how to do that. What we'll do is, let's try to find this command within API reference. So if you have that open, you can search for gravity. Okay, that's what I was searching for. So this is one of the options. It's called MG option. And it's actually present in mgmodel.h. And you can find this file in MuJoCo, I think it's included here, MuJoCo mgmodel.h here. So this file actually has all these things. If you want, you can refer to it from there, or you could also refer to it on the documentation. What I need to do here is actually go to gravity and modify the gravity from what it is. So it is 0, 0, minus 9.8 to maybe 0, 0, minus 1 if I want it to slow down. Now, how do I do this? Well, I need to see this belongs to MJ option. Okay, so I need to find if there's an object corresponding to MJ options. If I go to this file main.c, I search here, there is MJV option. So I need opt, and this opt is part of the model, right? Because if you go back to, since this option is part of mgmodel.h, I need to access option through the model, which means that I need to do put a pointer from it belongs to M, within which it belongs to opt, and then I need to go to gravity. So what that means is I need to, before I run this while loop, right here, I basically try to set the gravity to whatever I want. So here I'll set it to M opt. One sec. Yeah, so it should go, the syntax is M opt.gravity. And then there are three components, X, Y, Z. I'm only interested in modifying the Z component, which is the third component. So since indexes start from 0, it would be number 2. And then let's change it to -1. And now if I run this now, it should slow down the animation. So let's run that. You can see it went slowly. In fact, if you want it to stop, then you just put 0 and then it will stop. In this case, I'm not really interested in changing the gravity. Later on, maybe I might be interested, but let's now just comment it out. Okay, so you saw that the ball fell from its initial position, which I set in the XML file. I set it to Z position of 1. What if I want to start the ball from the plane? Instead of dropping it at 1, I start it at 0, 0, 0. I can do this by changing the file here. I can write whatever I want here, but every time if I want to go to the XML file and modify, it's too much work. If I can do it in the main file, that would be great. So there's a way to change the initial condition in the main file. And again, for that, you need to go to the documentation. So I kind of know what it is. This is one of the things which is hard to find with a keyword. So you need to do some digging or try a few things till you find the option. It's actually called qpos is what is used to specify the position. So it should, a lot of qpos. Qpos. Okay, this is the qpos I'm looking at. It's in data, and it basically gives you the position. And now here's something new, which is it's saying it's nq cross 1. NQ is the dimension of the state. Okay, NQ is not here. NQ. So dimension it NQ. Okay, there it is. So in the MJ model, there is an NQ, and that NQ is the dimension of the objects within that world which we created. Now the question is, how do you figure out NQ? What is NQ? In this case, I know it's a free floating object. That's all what it is in the scene. So NQ for this has to be the 3 translations and 3 rotations. And it turns out that MuJoCo doesn't like to use angles for the rotations, they actually use quaternions. There are 4 quaternions, and so NQ should be 7. Now, if you want to find this information, you can actually find it by doing something which I'm going to show you. What I would do is I would open simulate again, and you need to do this only once. So go to cd dot dot, go to cd bin, and once you're here, type simulate, and now drop the ball.xml file. Okay, what I'm interested in primarily here is to click on this print model. Okay, once I do that print model, if you go to the bin folder, you should see this file. It's called mjmol.txt. It was just created. In fact, it was created when I pressed print model. So we don't need this. So I'm going to close the simulate. I'm going to take this file, and I'll share this via chat, copy this file, go back to my projectile folder, and then just drop it here. And let me send it via chat. You don't have to do it yourself, but you know how to do it now that I showed you. Okay, I sent it. Now let's open this file. Okay, this file basically gives you all the information you need to understand NQ, NV. So NQ is 7, which means that in this there are 7 state variables. As I said, there are 3 translations and 4 for quaternions. NV, next variable, is for velocity variables. So if you know, there are 3 velocities, Vx, Vy, Vz, and then there are 3 angular rotations, omega x, omega y, omega z, that's 6. NU stands for actuators. We have not defined actuators, and so on. So there is a way to interpret this. And you can interpret this by just going to the documentation and searching for. So for example, if you want to see what N body is, that's number of bodies. So we have 2 bodies because we have the sphere and then we have the ground. N joint is 1, that's the free joint. So this is like an easy way of understanding the number of variables in that. Now, as you scroll down, you see other things like, for example, the time step, the integrator. 0 means something here. I think it means Euler. And then if you use the other one, it will be 1 probably. So we have a body 0, and it gives a lot of information about body 0, body 1, which is the projectile, joint 0, which is the free joint, and so on. So we'll actually interpret this file a little bit later. Right now, we kind of know that we're dealing with a free joint, which has 6 degrees of freedom. And so what we'll do is we'll just use that information to set the position. So we know that it's Q pos is what I'm looking for. Okay, that's the one. So I need to access this. And I said this is a part of data. So I need to access it through D. And so let me go back to this code and then access it. So D points to Q pose. And as I said, I'm trying to set, so Q pose is NQ. Q pose is dimension NQ cross 1, which is equal to 7 cross 1. So there are 3 translations plus 4 for quaternions. Okay, so the order is X, Y, Z. So I'm looking for X, Y, Z for the first 3 degrees of freedom, and then it's the quaternions, which goes actually as 1, 0, 0. The constant part is first. So in this case, I'm interested in setting the Z position from, it was set to 1 here. I want to set it to 0. Right? So I go to 2, which is the third component, equal to 0. And I can just run this. Not this. I need to navigate back to projects, projectile, and then run Unix. Okay, so there's actually, it shouldn't have, if it was exactly placed in the plane with the velocity of 0, it shouldn't have moved. The reason why it moved is because the radius of the sphere is 0.1. And so if I try to put it at 0, it's actually penetrating. And so there will be a collision, and that's why it moved. So if you want to make it not move, then you want to put this as 0.1 so that it's exactly above the floor. And this might actually also give some collision to see. Yeah, it did not move. That means that it's placed nicely on the plane. Okay, so we've got that. Okay, now we've got it on the ground. We want to launch it with a vertical speed. So we need to find the right way to launch this projectile. So again, if you go here, if you scroll to QPose, there is a QVel, which is the velocity, and that's dimension NV cross 1. So if you remember, NV was 6, corresponding to 3 for translation, 3 for rotation. So I need to set the Z velocity. So I set it to QVel2 equals, I don't know, let's put, say, 5. So it's 5 meters per second in the upward direction. Then run it. You see it launched itself with that speed. Okay. What if you wanted to launch it slightly in the forward direction, like a projectile? So in this case, I want to launch it in the X or Y direction. So if I do this, so the problem here is I do not have the axis, so I do not quite know which direction is X. So I can make a guess. So for example, if I could put 0 equals 1 and then see how it launches, and that's how I'll come to know yes, that it looked like the direction I chose for X was the right one. But if you wanted to see the axis, there's a way to do it. Okay, and this is, I'm not going to delve too much into it. I'm just going to give you the line of code, which I again found by looking at the documentation. So if you put, just before update scene, if you put op.frame equal to MJ frame world, it is supposed to show you the X, Y, Z axis of the frame, of the world frame. So if you do this now, you see it showed the axis. In fact, red is X, green is Y, and blue is Z. So we had the right direction. Okay, so we got that. Now, what about adding a drag force? So we want to slow it down. And so the model I chose to add a drag force, and so we'll add the drag force here. So every time step, we want to add some force which slows this down. So the drag force model I used is equal to, let's say, minus C times velocity squared. So it's proportional to the squared of the velocity, where velocity is the magnitude, times, so this has to be now given to each of the 3 directions. So we'll put a unit vector v. So it's going to be cv squared, but it's going to be act in the x, y, and z direction of the velocity. That's why the unit vector. So we can demystify it a little bit. V equals, so v is the magnitude of velocity. So that's square root vx square plus vy square plus vz square. Okay, and then the unit vector, the vector v is vxi plus vyj plus vzk. And since I'm interested in unit vector, it would be vector v divided by the magnitude of v. Okay, so what that boils down to is, if you do the math, that is, you take this unit vector equation which I wrote down and combine it with this and write it in this, you'll get 3 forces in the 3 directions. There'll be a force in the x direction, fx, which will be minus c times v times vx. So again, you need to do the math. Fy will be minus c times v y, and then fc would be minus c times v vz. Okay, so that's the force. Now, so this is nothing to do with MuJoCo. This is just the kind of drag model I chose to put. I need to put that force in the x, y, z direction. So there is a way to do that. If you, again, go to the documentation, you can apply an external force to the system by using this command called xfrc apply. It says apply a generalized force, and you can see that's nv cross 1, which means that's the dimension. So if there are nv corresponds to the degrees of freedom corresponding to the velocity. So Vx, Vy, Vz, omega x. We can apply those many forces. So in this case, I'm going to apply this in the x, y, z direction. So I copy that. Okay. When I put this, remember that this belongs to data. So the way I access this is d pointer qrfrc applied. Zeroth component should be fx. I need to define that, of course. That would be in y. And then last one in z. Okay, so I need to now define these things. So the velocity I need to define Vx, Vy, Vz. Okay, I need to get the values for the velocity. So how do I get the value? Well, again, you remember we set the velocities this way. It's the same way you access them. So in order to get the x component, we need to take the 0th component. And then we just do that for y and z. So y would be 1, z would be 2. Okay. Next, let's define this v, v, and then compute it. V equals square root Vx times Vx plus. I believe you cannot do Vx square the way I've written it here in C. Maybe I've changed it. Vz times Vz. So I need to do it this way. Okay, and now I did not quite define this, and it'll give me an error. So I need to define them first. Z, and now let me use it. But before that, I have this component C, which is the coefficient of drag. So C, I'm going to start off with a very small value, 0, 1, say. Okay, and now I'm ready to define fx, which is essentially this formula. So just copy this, paste it here. Okay, so let me run this. If it runs, I'll send you this code and you can paste this just below MJ step. Okay, there is an error. I have not defined C. Just define C. Okay, that didn't seem to have done anything. Unix. There it is. I mean, if you want to increase that the plane, it just goes beyond the frame, then you can just go to ball.xml, and then you can see this plane. It's right now set to 1 by 1, 1 meter by 1 meter. You know that it's moving in the x direction, so let's make it 10 in the x direction, and so you'll see it will be a little bigger. It's a little better. Okay, so let me just increase the drag force. Let me make it 0.2 and see what happens. So because right now it's not really looks like it's doing much. I think it looked like it was slowing down. Okay, so let's just keep adding the drag, keep increasing the drag. Okay, so you can see that the drag is actually affecting it. We can actually increase the speed now that we've got quite a bit of drag force. Okay, that was a bit too much. Let's go to 5. Okay, so I think it's kind of working, and if you can play with the drag. The last thing I want to tell before I stop was that here the ball has gone outside our view, and we want to ensure that it's always in view. And there's a very easy way of fixing that. What you need to do is you need to change the camera position. You need to move the camera as this ball moves. And what I'm going to do is, the simplest thing I can think of is, if you remember these options we took a look at, this is basically the X position where the camera looks, Y position, Z position. So if you want the camera to keep focusing itself on the ball, we only need to modify this one. So what I do is I take this, and this has to be put inside this while loop where I do update scene. This is updating the scene. So I need to put it here. All I need to do is set it so that it corresponds to the position of the ball, the X position in this case. Okay. So I change that and now run it. So now the camera is actually moving with the ball. You can actually, if you have a simulation where things are moving in various directions, you can pick which objects you're going to keep track of, and then you can just change the camera position by using this. So at some point, you can make it trace one object, and after some time, you can make it trace another one, but it's really open now once you have figured out that this is the command to use. So these are the commands we learned. The one which I used lastly was the one with cam. This is to assume this change where the camera looks, but you can also change where the camera is placed. So we change that to the X position of the ball. We looked at how to change gravity. We looked at how frames can be used to show the frame. You can actually show the frames of different geometries also if you want to. We also saw how to set the initial position and velocity, but not only that, we could actually access the position velocity at any point of time and introduce track force as needed. And then we saw how to apply an external force using QFRC apply.